In our previous few videos, we looked at graphing rational functions by finding vertical asymptotes and finding horizontal asymptotes, finding the x and the y-intercepts, and then by graphing some additional points to see what the shape of the graph was. In this video, we're going to talk about the concept of holes. Let's look at the function f of x equals x squared plus 4x minus 5 divided by x squared minus 4x plus 3. And this is a rational function because it has a polynomial in the numerator and a polynomial with x in it in the denominator. Our first step is going to be to completely factor the numerator and the denominator. These are both quadratics with no coefficient on the leading term. So we know we're going to have x and x, and we can find two numbers that multiply to give -5, add to give +4. And then in the denominator, go ahead and factor that one as well. Take a few minutes and do that. Go ahead and stop the video if you need more time. All right, two numbers that multiply to give me -5 and add to give me 4 are going to be +5 and -1. So that one is that factorization. On this one, on the denominator, we have two numbers that multiply to give me +3 and add to give -4. To get a +3, they both have to be negative. So I have an x, and they both have to be negative to have a positive here and a negative here. And I see those are going to be 3 and 1. All right, now notice on this one, notice that these two factors are exactly the same. That means that I could cancel those two factors, and I'm going to have that is equal to x plus 5 over x minus 3, except when x equals 1. Notice that if I plug 1 here and here, I'd get 0 over 0. So if I actually were to find f of 1 from this original function, I would have 0 over 0, which is undefined. That means that this function, f of x, does not exist when x equals 1. That's what gives me a hole in the graph. So what we're going to do is we're going to recognize that we have a hole in the graph because of this factor in the numerator exactly the same as in the denominator that canceled out. So our process will be to keep that in mind. We'll come back to that in a minute. And we're going to actually graph y equals what it would be without that factor, x plus 5 over x minus 3, which I found up here. So we're going to graph that. And we're going to use it, do it the same way, finding our vertical asymptote, our horizontal asymptote, x-intercept, y-intercept, and maybe some additional points. And then we'll see what happens with the hole after we do that. So I want you to go ahead and do that. I want you to go ahead, find your vertical asymptote, find your horizontal asymptote, find your x-intercept, your y-intercept, and an additional point or two. Plot all of those on the graph, show the asymptotes, etc., but do not draw the graph yet. Just put all the information you know so far, but don't try to graph it yet. Go ahead and turn off your video, pause your video, and do that work, and then we'll start back up in a minute. Okay, so for my vertical asymptote, I'm going to set the denominator equal to 0 and solve for x. So 3 is my excluded value, so my vertical asymptote is x equals 3. Then I'm going to, for my horizontal asymptote, I'm going to look at the coefficients of the leading terms. Excuse me, I'm going to look at the degrees, and I see they are the same. So that tells me I'm going to look at the coefficients. I have an understood 1 over understood 1. So my horizontal asymptote is y equals 0. For my x-intercept, I'm going to set the numerator equal to 0. Oops. And I get x equals -5. So I have the ordered pair -5, 0. My y-intercept, I'm going to plug 0 in for x. And I end up with 5 over -3, which is -5/3. So I have 0, -5/3. All right. I don't know yet which, excuse me, which additional points I need. So I'm going to go ahead and put that information on my graph. Vertical asymptote at x equals 3. Oh, I wrote something wrong here. Okay, this should be y equals 1. I said 1 and I wrote 0. So y equals 1, because remember the coefficient here and here were 1 over 1 because the exponents were the same. So our horizontal asymptote is y equals 1. And then I can plot my x-intercept and y-intercept. I've lost my x-intercept. That was over here, 3. So 3, 0. No, that's not right. That was my vertical asymptote. All right, so this was the work here, setting the numerator. So that was my x-intercept. Here. And my y-intercept was 0, -5/3. -5/3 is -1 2/3, so about right there. And I have those 2 points. Now that's going to lead me to believe that the curve is over here on the left, on the bottom, but we are not going to draw that curve yet. We're going to do the hole before we draw the curve. So I can see where that curve is going to be, but I need to see where the curve is over here on the other side, on the top or the bottom. So I need a point over here, somewhere beyond the vertical asymptote. I'm going to go ahead and do 4. So when I find that, remember we're plugging back into this graph, the one it looks like everywhere except at x equals 1. So since x equals 4, we can plug back into that, and we have and we have 9 over 1, which is 9, so we have the ordered pair 4, 9. Now, if we plot that point, 4, 9, over here, here's 4, y is 9, and we have that ordered pair. And what that does is it lets me, that's a point on my graph, so that lets me know that my curve will be up to the right there. Okay, let's go back and revisit the hole. The hole, remember, was at x equals 1, because that was the value of x here where the 2 factors canceled out. That was the value that gave us 0 over 0, which was undefined. So if we go back and we find out where that hole would be, if it could be there, we're going to plug the x equals 1 back into what the function looked like after we did the canceling. So we can plug the 1 in. And we get our whole is going to be where x equals 1 and y equals 3. Now, if this were the actual graph, that would be a point at -3. That would be a point, an ordered pair at 1, -3. This is 1, this is -3. But that is not a point on my original graph because the function does not exist for that single point only. So what we do is we draw an open circle right here at 1, -3, which is where my hole is. And then I see that the curve, instead of just going right through that hole, is going to jump over that hole. And I'm going to have a curve that looks like this. And we'll pretend like that touches right there on that. And then up here on the other side, I don't have any holes or anything to worry about. So I draw my curve up there. All right, so that's how you do a hole. Let's kind of recap here. I can recognize when I have a hole if I completely factor the numerator and the denominator. And I see that I have two factors that are exactly the same that will cancel. So whatever value of x makes that factor equal 0, that is going to be where my hole is. So I set that aside for now. I look at the remaining function and I graph it using the methods that we've learned so far. Now this one turned out to be a rational function. It could be a line. If the denominator completely cancels, you could have a linear function, and you can just graph the linear function using those methods. But this one is still a rational function. So we find the vertical, horizontal asymptotes, xy intercepts, additional points, etc. Graph it just the way we normally would, except for the hole. Now we go back, look at the hole, think about if we could have x equal to 1, plug it into the function after we did the canceling, see where that point would have been, and then draw it as an open circle. And then we can draw the rest of our curve as we would have before.